Hello, everyone. My name is Kevin Diaz, and I am a senior physics major at Virginia Tech. And today I will be presenting my research on material screening with high purity germanium detectors. And so the objective of my research was to characterize the performance of the VT1 and VT2 high purity germanium detectors at Virginia Tech for material screening and to determine the cobalt-60 activity present in two steel samples. However, due to COVID-19 restrictions, we were only able to use the VT2 high purity germanium detector. And we are particularly interested in cobalt-60 due to how it is a common radionuclide found in steel, resulting from nuclear weapons testing both during and after World War II, and also from changes in steel processing techniques. And so in this work, we will present the results of a search for cobalt-60 contamination into steel samples, one purportedly dating prior to World War II, and the other being a modern day steel sample. And we will be using the VT2 high purity germanium detector in order to search for any of the cobalt-60 contamination. And so here you can see images of those two steel samples. To characterize the VT2 high purity germanium detector, we determined the detector's energy resolution, energy reconstruction bias, and its absolute detection efficiency, in which we calculated the absolute detection efficiency using a Geon4 simulation of a potassium-40 source, in which a preliminary plot of this is shown. We calculated these three things in order to better understand the quality of the VT2 data. Here you can see a rendering of the VT2 detector showing the detector's crystal within the sample volume, and also showing the copper shield and lead shield of the VT2 detector that are both used to minimize the background radiation within VT2. Alongside it, you can see a real-life image of that same detector, where this is the sample volume, and that is the detector crystal. We then collected several days of data with an empty detector chamber to construct the VT2 background spectrum, shown here with labeled peaks that originate from common radionuclides, such as lead-214, bismuth-214, and potassium-40. We also placed the steel samples within the chamber of VT2 to obtain a spectrum for each sample as well. And so this plot here shows a superposition of those three energy spectra that we obtained. Notice that there is a background rate of cobalt-60 present within the VT2 background. This background rate most likely originates from the cosmogenic activation of copper within VT2's copper shield. And so this cobalt-60 background rate serves as a baseline of comparison to compare the counting rates of the steel samples with. To obtain the counting rates of cobalt-60 in the VT2 background and steel data, we fit both the 1173 keV and 1332 keV peaks of cobalt-60 for each of the spectrum using root to obtain the total number of counts for each peak. And this plot here is simply a zoomed in version of the one above. And these two plots here show an example fit of the 1173 keV and 1332 keV peak within the VT2 background spectrum. Once we obtain the total number of counts for each of these peaks for each of the spectra, then we normalized the counts to time to obtain the counting rate. Our results are summarized in these two tables in which they show that for each of the cobalt-60 peaks, the counting rates obtained for each of the samples are consistent with the background rate obtained for the VT2 background. And so we placed an upper limit on the cobalt-60 activity of the steel samples by calculating the MDA for the samples using this equation here. And so in conclusion, we did not find any cobalt-60 contamination within the steel samples. However, since VT2 is the sensitivity of VT2 is limited by the cobalt-60 background rate, future work will seek to replicate this experiment at the Kimballton Underground Research Facility near Virginia Tech, in which we will use the VT1 high-purity germanium detector that is located underground at KERF at roughly 300 meters water equivalent. The overburden provided by KERF will reduce background radiation levels caused by cosmic rays that we see in the VT2 surface detector. And so this plot simply shows a comparison between the VT1 background and the VT2 background, in which we see that the background is reduced by about a factor of 10. And finally, these are the references that I used throughout my presentation. And I would like to acknowledge funding from the US Department of Energy and from the Spencer Foundation for helping making this poster presentation possible. This is my contact email address should you need it. And I look forward to seeing you at the poster presentation. Thank you.